Okay, so this is problem 3 of our torsion chapter. And what we will use today is this twist angle and how it can help us solve for indeterminate system where the equation of freedom is not enough. So exactly as we did with the axial load with the delta, we will use this angle of twist. So what's happened is like when the torque is applied, so there's a torque that is applied like this rod on that side will twist on to, let's say, um, clockwise or counterclockwise, depending on which one you look at. And let's say this one is sigma A, and this point also belongs to this one, and that will be your sigma B. So what we can say is like, oh, not sigma phi, phi A equal phi B, and that will give us a new information. I say phi, I think most of people say phi, okay, because it's PHI. I say phi because it's a Greek letter, but whatever. If you hear me say phi or phi, that's the same thing. So what we will use and what do we have? So we know that the torque that is applied is how much do you want? 25 kilonewton time meter. We know that the distance A is, I don't know, 20 centimeters. We know that the distance B is 50 centimeters, and we know that the diameter is, let's say, 10 centimeters. So it's a bit longer than it looks. We also know that the material is the same. So that means that G is the same for the bar all the way, okay? Let's say the same bar, it's just one long bar. So we have all of that. So equation of equilibrium, step number 1, and we have all those equations there. Let me move them all the way there. So we keep them in mind, but we don't need them right away. So our equation of equilibrium, what does that give us? That give us, so what we try to do, we know the force T, we know the torque T, and we try to find the torque. Oh, let me make it in red because we try to find it. We try to find the torque TA and TB. And why do we need them? We need them after that to find the shear uh, in the pipe and where it's maximum. Okay, so if we solve this equation, if we write this equation, we have TA plus TB minus the T in the middle, that is 25 minus 25,000 equals 0. So we get TA plus TB equal 25,000. Okay, this is our equation 1 for the matrix. I always plug that in the matrix. I know you like also to substitute, doesn't matter to me, but I recommend matrix, it's way easier. Equation number 2, what we will use is first we will write phi A in terms of TA using this equation there. Okay, so phi A equal TA times LA divided by GA JA, and phi B equal TB LB divided by JB GB. Okay, we have those two equations. And number 3, we can say that phi A equal phi B, because again, this value there, this little twist angle is the same. Okay, they're attached together. So using this one, we can say that TA LA divided by GA JA equal TB LB divided by GB JB. Okay, this is the same materials, so GA GB is the same. This is also the same diameter everywhere, so GA and GB is the same. This is the pi divided by 2C4, and LA, that will be the distance A, that will be 20 centimeters, so 0.02. No, 20 centimeters, so 0.2. And LB, that will be the 50 centimeters, so that will be 0.5. Yes, don't mix up the mistakes, the value. So we get equation number 2, we get 0.2 TA minus 0.5 TB equals 0. This is my equation number 2. So now I use my two equation and my 1 and 2. So I use my equation 1 and equation 2, and I plug them in the matrix. So I have TA, TB equal 1 TA plus 1 TB equal 25,000. 0.2 TA minus 0.5 TB equals 0. I take the inverse, I multiply by this matrix, and I got TA equal, TB equal, and I didn't made it yet, so let me do that. 1, 2, 3. The first distance 0.5, and that is so. If I don't say anything wrong, I got some very strong torque. I got 17,857 Newton time meter and 7,143 Newton time meter. So this is 17.8, even 1.9 kilonewton time meter for this one. And we can keep it, or we can say 7.14 kilonewton time meter. So last step, we found tau, that is equal to the torque time the distance from the center. Just want to make sure I write it, so that will be the diameter divided by 2 times the J. So the diameter divided by 2, this is equal to C, okay? Because us, we have the diameter that's proof given. So tau at A will be equal to 17.9 times 1,000 to get Newton time meter. C, the diameter is 10 centimeters, so the C, oh, we have it there, 0.05, and divided by the J, so J equal the pi divided by 2 times the C at the fourth. Not the C, the diameter divided by 2, so the radius at the fourth. In our case, C and the radius is the same because we want the highest shear, and the highest shear will be all the way there. Okay, so we will be at, this is the 0.05 meter. Okay, and we get 90.9 times 10 at the 6 Pascal. That is 90.9 megapascal. Okay, so Pascal, Newton per millimeter per meter square, and we want Newton per millimeter square, so we need to divide by 1,000,000. For B, this is tau B equal the maximum torque 7.14 times 1,000. The diameter is the same at T and TB, so times 0.05. The C, that is the diameter divided by 2 because the shearing is the highest at the outside of the disc, the rod, and divided by the same J, pi divided by 2 times 0.05 at the fourth, and that gives us 36.4 times 10 at the 6 Pascal, 30.4 megapascal. 36.4 megapascal. So here we go. To find the maximum shearing stress in a rod that is submitted to torsion, we use tau equal T times C divided by J. In this example, we had to find first the torque, and we use the compatibility of the theta of the angle theta B equal theta B because it's a statically indeterminate problems. So I hope that makes sense. Let me know if you have questions. Bye-bye.